Welcome back. We're going to finish up Chapter 8 in this segment, introduce Chapter 9 in our next one. We need to talk about physical properties of haloalkanes. First off, they're not very polar. I want to make that clear. Even though we're going to discuss polarity first, they are not polar. Which means they will not dissolve in water. Which is a good thing. We can take advantage of that. They do have a small amount of polarity based on the fact that one of their bonds is polar covalent for here and here. And our description of polar covalent doesn't work down here. Why was this one polar covalent? The difference in electronegativity, remember those? Delta En, 4 minus 2.5, 1.5. This is on the limit of polar covalent. 3 minus 2.5, 2.8 minus 2.5, and 2.5 minus 2.5. So you'd say, why is that a polar bond at all? And that's a good question. We'll talk about that shortly. So in terms of the most difference between electronegativities, you would predict, based on your previous knowledge and understanding, you would predict this to be the most polar of these four bonds. You would be wrong. I don't like that. Because only half the story is the electronegativity difference. The other half of the story is if you can get charges separated by a greater distance, then you've also increased polarity. And the fact is fluorine is very small, so it's not very far away from the CH3 here. The bigger chlorine, the center of its nucleus, has to be further from the carbon because it's a bigger atom. And that's quite a big jump between, this is the distance between the two nuclei. We call it the bond distance. 178 picometers is what that is. 139 here. That's a jump of 40 picometers out of something that only started at like 140. It's a little more than a third, a little less than a third. But that's quite substantial change, a third. And this one only goes up by 20, not even 15. So it's not a big percentage change. And similarly here. But that's a significant factor. In fact, the units of polarity, they're over here. They're called dBi. And it's two factors that are equally important. Charge, so the amount of charge is dependent on the electronegativity difference. Dependent. Oh, wow. I changed the spelling of dependent. Okay. Now, distance is dependent on how big the atom is. That's clearly going in the opposite direction. The biggest atom has the lowest electronegativity, and the smallest atom has the largest. So we have two different factors going in opposite directions. And the happiest medium is this one right here, where the atom is still not particularly large. And it has a high electronegativity. So that's the happy medium. Happy's a poor choice of word. Medium between, yeah, I'm going with happy. Why not? We need happiness at these times. Happy medium between I got to get the W between the T and the E. Happy medium between distance and delta En. It's got a pretty good delta En, and the distance is pretty far. Okay, we jumped up quite a bit here, although we sacrificed the delta En. Take home message, very simple. Take home message. Chlorine. Chlorine. Okay. Chlorine forms, wow, I'm having a good typing day. Forms the most polar CX bond of all the halogens. Don't get me, don't overread that. It doesn't say it's polar enough to make the molecule polar, but of the 4 halogens, chlorine's getting you the most polar. And there you go, put that in purple, make it pretty big, move it, be done with it. Okay, maybe not move it. Okay. And haloalkane solvents are quite commonly used in lab, although they're all suspected carcinogens, so they have to be dealt with appropriately. Just because some molecule causes cancer doesn't mean it can't be a useful molecule in the lab with the proper safety precautions. So ventilation and gloves and not exposing yourself to these chemicals is a good way out. Sometimes you want an extraction solvent to be the bottom layer during an extraction. This is a typical diagram taken straight from the textbook. It's called a separatory funnel. Somebody left this one on, so right now it would be dripping down here. You got stuff would be falling out of there. I couldn't find a diagram where it was closed. So somebody brewed up a pot of coffee and put it in here. And then they added dichloromethane because they want to extract the caffeine, which is a non-polar molecule, out of the water. And this would work. So what he does is he seals it up. He puts a little stopper up here. A little stopper. And he shakes the things so they get nicely mixed together, lets the layers settle down. Why does dichloromethane go to the bottom? Because of something I forgot to discuss over here. No, I didn't. I just didn't put it here. I'm putting it over here. Why is it the bottom layer? Halogen mass is high compared to its volume, atom volume. My favorite example is a CH3 taken together has about the same volume as a Br. Almost same volume. Remember, density is why things sink or float. So don't talk to me about mass. Talk to me about density. So V equals X. So to do density, 15 over X compared to 80 over X. Where'd I get those numbers from? It's our friend, the periodic table. 1 carbon and 3 hydrogens weighs 15 grams per mole, roughly. And 79.9 for bromine is very close to 80. And yeah, it's going to be what, 5 times 15 is what, 75? It's 5 times heavier in the same volume. Guess what? 5 times as dense for this portion of the molecule, whatever it's attached to. So yeah, halogenated solvents are denser than water. So it puts them at the bottom, which is cool. What you would do is you do this experiment as depicted here, then drop the bottom layer out of there. So you'd be left with the water still in there, still a teeny bit of caffeine in that water. My lab students will say, well, you want to get all the caffeine out, do 3 extractions, don't just do 1. So it's nice to have the bottom layer be the organic, drop it out, put it somewhere else, add more dichloromethane here, shake, 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 vent, vent, vent. And then extraction number 2, put the bottom layer with the other bottom layer and extract your water a 3rd time and put all 3 bottom layers together, evaporate the dichloromethane, and guess what you got? You've got all the organics that are left in the coffee. Caffeine's then the principal organic that would be after you've evaporated your solvent. So we love extracting things out of molecules, whether it's natural products, you're extracting vanilla out of the vanilla bean, or you're extracting paclitaxel out of the pine needles for making the drug doxorubicin. Yeah, these are extractions of very common science that we have to become good at in the lab so that we can do it in real life. And then we have this cool page from the book, generated from a student idea. We've looked at why cations are more stable if you have more carbon groups around them. We called it hyperconjugation. Hyperconjugation. And what we didn't say was not only does it stabilize cations, but it also stabilizes radicals. And it explains why an alkene with more carbon groups around it is more stable than an alkene that has less carbons around it, because hyperconjugation stabilizes any kind of p orbital, whether it's a cation containing p orbital. I don't like the way I said that. The p orbital is empty, which causes it to be a cation. And hyperconjugation stabilizes that by putting electrons close to it. A radical is only a half-filled orbital, so it needs help with electrons nearby as well. Hyperconjugation provides that help. And pi bonds have p orbitals as well, which need stabilization, and having sigma bonds with the right orientation, hyperconjugation, allows them to be stabilized as well. And we call this the crap page because cations, radicals, and we don't usually use the little words, but CRP isn't a word. Cations, radicals, and pi are stabilized by what? Hyperconjugation. And it explains definitely the trend here, where we have tertiary, secondary, primary, methyl. Methyl, the product you're about to make, the radical, has no hyperconjugation. So remember, we're comparing these molecules where there's a radical. No hyperconj. And this one has the most hyperconj. And explains, that's a weird J. It explains cation stability, radical stability, and pi bond stability. And I think that's the end of chapter 8 material. And that would be a very short segment. I don't think you would mind. I'm going to hunt around for more chapter 8 material. And if I don't find it, then we're going to have a nice long chapter 9 introduction. If I find some chapter 8 material we didn't do, we'll start with that and then do our introduction. We'll see you then.